5G is undeniably coming, but to get there, we have to solve some unique design and test challenges. And that's what we're going to explore in today's Double E's Talk Tech podcast. Hi, and welcome to Double E's Talk Tech. My name is Daniel Bogdanoff, and I'm joined by a couple other folks. Could you guys introduce yourselves?
Sure. My name is Greg Acey.
Hi, everybody. My name is Joe Haver. I'm the product manager for our new high-performance UXR oscilloscope.
Yeah, so Joe gets to play with our new 110 gig scope and lower bandwidth all the time. But the 1 gig is kind of the cool, or the 110 gig one is kind of the cool one. But it goes all the way down. How far down does it go?
Well, I mean, it really goes down to DC. So from DC,
well,
all the way down to 10 gigahertz.
Okay, fine, sure. That's not the question I was asking. But we're not here to talk about scopes. We're here to talk about 5G. And not just 5G overall. There's been a lot of podcasts about 5G and a lot of articles and videos out there. I wanted to hone in on a couple specific things today. So first, 4G, my first question, 4G was pretty much all sub 6 gigahertz as far as the technology goes. Is 5G the same way, or are there higher frequency bands?
5G is quite a bit different than 4G. I mean, not only do you have the sub-6 frequencies, you also have things in the millimeter wave. So we're talking about like 24 gigahertz, 28 gigahertz, 39 gigahertz, and even to be determined greater than 50 gigahertz frequency ranges. So it really does change the playing field in the mobile communications area.
Okay, so that's getting really pretty high up there. Has the FCC already allocated those spectrums, or are there negotiations happening, or what does that look like?
Yeah. So I mean, there are negotiations happening, but the 24, the 28, and the 39 have kind of been allocated. There's still some to be determined frequency bands, which means you need a lot of flexibility when you're talking about your future direction and capability to not only handle what's already allocated, but what's going to be coming in the future.
Okay. So designers looking to roll out, when they were rolling out 4G, what were they using to make sure everything worked? Like what, from a test tool standpoint, what did that tooling and bench setup look like, or the assembly line, manufacturing line process look like, and what tests and strategies were people using to make sure that those systems were functional?
So I mean, a lot of times you just start to make sure that it was functional. You'd start with a simple source. So you'd want a source that was really clean, and then you didn't need like the top of the line spectrum analyzer to be able to do it because you're sub 6 gigahertz. So kind of a middle of the line spectrum analyzer would work well. So, I mean, at the very fundamental, what you'd have is a source and an analyzer, to transmit and to receive and see what exactly was happening. I mean, you could see some complicated things with an instrument known as a VXT, which is a transmitter and a receiver together in one instrument, and then there was a bunch of component blocks that were switches and things like that to be able to test the different carrier frequencies. But for 4G, I don't want to oversimplify it because there was a lot of other things, but at the very fundamental, it was a source, an analyzer, and not at the highest frequencies. You didn't need the best of the best to test sub 6 gigahertz.
Sure. So, and 5G is not just a simple rev of 4G. Like, it's a brand spanking new technology. So what's a 5G test setup going to look like? Hey everyone, I wanted to quickly interrupt our normally scheduled programming to bring you this message. We should fix that in the script. Also, we should get a massage. Anyways, the team put together an awesome new ebook called Tech Trends, which explores how to prep for new technologies like DDR5, C6, PCIe, Thunderbolt, PAM4, and more. Go to doubleestalktech.com and download it now. It's free. So what's a 5G test setup going to look like?
A 5G test setup can now have a lot of similar components. Of course, you have you have to have your signal generator, but you need some more powerful signal generators because the carrier channels are actually a lot larger now. We're talking like FR2. You're talking about 100 megahertz, 200 megahertz, 400 megahertz wide bands. So you need something that's capable of doing a really high quality, wider band signal than you would run into in a 4G type environment. So that's one major point that you need to consider.
Okay.
Yeah. The other thing to a lot of over the air type testing, and so a lot of people are having to go in, grab chambers to go and do their testing. The other thing that makes 5G is things like multiple input, multiple output. There's a lot of MIMO testing that's going on, even sub 6 gigahertz right now with 5G. And so what was simple before was, maybe one channel, possibly two. And now people are talking about 64, kind of MIMO measurements. And so how do you test all these different channels? Like Joe said, fundamentally it starts the same, but when you look at where it's going, the test setup to make sure it's still working, it gets a whole lot more complicated with 5G.
Yeah, not to mention, it's not like you're sub 6 or only 28 or only 39, right? If you're designing a 5G element, it needs to support all of these frequency ranges simultaneously, potentially. So you need test tools that can actually cover that really broad range of bands.
Okay. You mentioned MIMO. Can we touch on that? Or multiple input, multiple output. Can you briefly touch on what that is and why that's getting implemented for 5G?
Sure. So I'll talk and then you add if that works.
Okay,
so you think about like a 5G signal, right? You have an antenna, and one of the things that they talk about is beamforming and being able to look at multiple signals coming into the antenna from multiple directions, right? And so the beams kind of move. And with 5G, what you really want to do is test and see all of these signals at once. And so because of the complexity of a 5G network where you have so many different signals coming in, you have to be able to test to understand what's going on if this signal comes in here and this signal comes in here. What is the interference? What does that look like? And so as a result, instead of just focusing on a single channel now, we're having to look at these multiple channels and really looking to see, is my 5G system playing like it should be playing?
Because one of the things 5G does, 4G is kind of just a spray and pray where it's kind of most places all the time.
Yep.
Where 5G is more of a targeted, as I understand it, like a targeted beam that's going to your receiver.
Correct.
Yep.
So you touched on beamforming. Can you expound on that a little bit? If not, I know it's like a super complex topic.
Yeah. So imagine your omnidirectional antenna, right?
Sure.
We're talking Wi-Fi now. All right. Let's go start off at the very easy. You basically have an antenna, and it's putting out a circular donut of radiation, which is going out to all the different UEs that are out there. When you start talking about 5G, you're talking about beamforming, where now instead of having this omnidirectional antenna, you basically have this array of, I'll say horn antennas as an example. And you can have these arrays of, let's say 4x16 or, et cetera. There are lots of different array sizes. And each of those antennas now can actually have a directional beam associated with it. So by using each of these individual horns inside this antenna, you can actually point each individual beam at a specific UE. What this means is now the amount of power I have. Here's the challenge, right?
What is UE?
A UE is the endpoint. It's
like
an
end user.
Yeah.
Okay.
Yeah, it's the device.
Okay.
It stands for user equipment.
User equipment.
Yeah,
Okay.
sorry. So it's actually the cell phone. In this example.
Sure. Yeah.
And what happens now is, in that omnidirectional example, I only had, let's say, 1 watt of power that made that entire donut of radio.
It's spread out evenly over
Spread out evenly, kind of
more
in a
or less.
circle.
Yeah.
Right. Now with beamforming, I now actually get to take that power and direct it all towards one device. This is very, very important. As you start to go up in frequencies, the range that you gets lower and lower because of the atmosphere and other interferences. So by being able to focus all of my power specifically at the mobile device that I want to target, gives me more range, which is going to be critical in a 5G environment.
Okay. Yeah, it's actually, I was looking into it a little bit, and basically with beamforming, you can aim your signal, like you can aim your signal out of your antenna using like slight phase differences between two signals, that it's basically constructive and destructive interference. So you can actually aim your signal without physically moving
Turning the
your antenna.
Correct.
Yeah.
Yep.
Yeah, so I kind of picture like, in action movies, there's a real cool thing for a while where they like take the gun and they shoot and like twist it at the same time, and the bullets it's kind of like that, where it's like this super complex like targeting using basic properties of waves, right?
Right,
That you can target it into a specific
Yeah,
area.
that's correct. It's very Matrix-like.
Really cool. Yes, it's just like the Matrix.
Yeah, I see Keanu Reeves with his UE like bending over and the wave coming over.
He's trying to
slowly
like
over his
get 5G signal because the signals won't go through his hand, right?
Right.
So handsets, is 5G going to be kind of is it for cell phones or where else is this technology getting implemented? Because I know there's a ton of different flavors of 5G.
Yeah, there's lots of 5G. I mean, the handset is of course the obvious thing, right? But think of it this way: mobile carriers haven't been able to actually target or access the residential market because of the infrastructure running copper or fiber to homes.
Right.
5G promises, you want to say, wired type of speeds without the wired type of infrastructure.
Yeah.
So it's going to really open up brand new markets for operators that they never really had. I would call it viable or economically viable options to get to that market. So there's going to be a whole new area there. And then of course, I mean, self-driving cars, the ability for cars to actually make decisions. You need a really fast, really high bandwidth network. I mean, there have been talks.
So basically, you take sensor data from the car, you send it to some processing unit somewhere, or like a cloud-based like aggregate computing that looks at all the cars, or what is the need for?
I don't know if that's really been defined yet.
Okay.
But the need for the cars to be able to communicate very fast, not only to the cars in the immediate.
Oh, you could do car-to-car communication with that.
The car-to-car could talk to each other, but also cars a mile down the road are warning other cars down the road of what's happening around them. So there are those types of applications that 5G can also enable.
I was actually a couple weeks ago, I was talking to someone and they were talking, what's the big deal about 5G and security, right? So, I mean, we continually hear about the problem that, hey, we're concerned about 5G and others in the security piece of it. And one of the reasons is even something as simple as agriculture, right? You would never think of 5G as an agriculture kind of play. But when you think about, like, we're trying to get more and more food out using the same kind of land, right? So the population's growing, so we got to get more food. Well, so sensors inside of the agriculture to control, like, the water, make sure you're absolutely maximizing everything to maximize your crop growth. You need that 5G network to be able to push that much data, to be able to crunch that much data. And so even though you would never think about a cellular network in agriculture, it's just one more use of why 5G is so important to us.
Interesting. Okay. Way back when we started talking, you mentioned the bandwidths of the signals. Where were we looking, what were kind of our bandwidths? And bandwidth in this case, I mean like the width of the communications channel for a given technology. What were the widths in 4G? And you mentioned higher ones down in 5G. And is that a problem for engineers, or like it seems kind of like it's new uncharted type territory for test?
Yeah. Well, let's talk a little bit more about RF. So as your carrier channels get wider, the wider bandwidth that anything uses, the lower or the more interference and the lower, when you say, effective number of bits that you get going across that particular particular channel. So as we look at 5G being these 100 megahertz, 200 megahertz, 400 megahertz channels, you actually get more interference across that wider band. So it's actually harder. Though you get more data throughput, you actually have to have more sound engineering and developing your radio system in order to be able to carry those wider band signals through the air.
So is it a filtering challenge, like filtering out sidebands, or what does? What's causing that extra interference?
I mean, it's a filtering challenge, but in addition to that, it's just the wider band itself. You basically lose more power of your signal. It gets the power that you have available gets spread across a wider range, and now your signal to noise ratio gets reduced, which means you can have more bit errors and those types of things.
That makes sense, because
we're talking 1.4 gigahertz of bandwidth inside of the 5G signal, right? So you have 100 megahertz carriers, 200 megahertz carriers, but it's across 1.4 is what we've heard. Some of the big companies have said we're going to push after 1.4 gigahertz. We've also heard, hey, look, we want to go even wider than that. But that's a really wide signal for a telecom type communication.
Yeah,
especially over distance. For like Wi-Fi, it gets a little bit easier because it's in room. But now we're talking about kilometers of distance that the signal needs to actually carry over.
Well, and couple that with the really high frequency of 28, 39 gigahertz that naturally doesn't go through walls very well. Right.
Or raindrops, or exactly. Like rain fade is a term I came across.
Rain fade. Tree fade in the summer.
Like, oh man, you put your houseplant, in the wrong place in the backyard, and now you your internet, it's only 1080p instead of 8K. Uh-oh.
Right.
The good thing is 5G will help you get the right amount of water to your plant. And so you'll be fine growing your plant as high as possible.
It'll just bounce it off the neighbor's house.
That's right.
Yeah, okay. But even like Windows pose a challenge here, right? Like trying to get some of these high frequency signals to an actual receiver that's not mounted like on a roof seems like it's a potentially pretty big challenge.
Yeah, true. Yeah, for sure. Which is why this beamforming comes in, because everything, even the air is going to pose a challenge for the signal itself. So that's the reason for beamforming in 5G. Again, you got to get more power directionally pointed at the UE in order to actually get that effective communications.
Okay. You mentioned the overall channel, like allocated spectrum for 5G being, maybe 1.4 gigahertz wide in certain places. How do you? I assume that when you're testing a signal with a signal or spectrum analyzer, you don't want to just look at like your 200 megahertz wide channel. You want to look at the whole spectrum that you're potentially using. So what are the options there?
So it kind of depends, because there are cases where you just want to look at, one band, so you want to look at 100 megahertz and just see what it's doing. And you look at each one of them individually. And so, in that sense, you're really testing similar to what you were testing back in 4G world, because you're similar in these 100 megahertz carrier bands. But, you do want to look and see what the whole thing's doing, right? So that 1.4 gigahertz, how are each of these playing together?
Right.
And so that's where 5G testing, we mentioned MIMO, but then you also have this challenge, and Joe's alluded to it a couple times, which is the SNR, or the signal noise ratio, pushing across 1.4 gigahertz. And then the other challenge is there's equipment that can measure, greater than a gigahertz wide analysis bandwidth there's not a lot of pieces of equipment that it can actually do it. And there are cases where you do want to see what that whole thing's doing and how everything's playing together, and, what are the distortions we're seeing, and things like that. How are they playing nicely together? And so it poses a whole nother challenge. And then again, couple it with MIMO, couple it with beamforming, couple it with all the other things. And I mean, it's tough. 5G is a tough thing to test.
Well, and I think specifically MIMO. I mean, think about this. You have the sub 6 all the way up to defined right now 39 gigahertz. You need to be able to look at all those simultaneously. Well, now you don't want to digitize 39 gigahertz worth of bandwidth.
Right, you get a ton of noise.
There's a ton of noise and a ton of superfluous information out there. Right. What you want to do is basically have like multiple different channels capturing the specific frequency bands that you're interested in. But if you look at a traditional spectrum analyzer, what's it got on the front? One channel.
Right.
So how do you look at let's say 4 distinct different bands simultaneously? This is where like the paradigm of testing is changing a little bit, and we see like oscilloscopes coming into this market that used to be dominated solely by spectrum analyzers, because an oscilloscope by nature has multiple channels, and if I can tune each of my channels to the specific bandwidth that I'm interested in, then the oscilloscope becomes a very viable tool, especially in a 5G environment.
And that's something you've been working on with the UXR, is some like filtering to essentially take. Oscilloscopes have always done DC up to their spec bandwidth, but we're working on some ways to actually filter out those lower frequencies and just hone in on a specific band.
Right. Yeah. Yeah. The UXR is an extremely powerful tool because of its ultra low noise. It makes it very, very good for, like say, DANL at these specific bandwidths for 5G. So now you can take your oscilloscope with 4 channels, and I can look at sub 6, 28, 24 and 39 simultaneously into the scope, and then get
cool.
EVM results. And we've done some testing right now on 100 megahertz wide carrier channels, and we're seeing EVMs of 0.5% EVM.
Wow.
Which is a spectacular result. And when I show people that,
EVM is error vector magnitude. So basically, you have a point that you're hoping to get to, and the distance from your actual sample point to where you're supposed to be is your error vector, and the magnitude of that is EVM.
EVM, exactly. Yeah. And we've seen our customers look at this and say, wait a minute, this is an oscilloscope giving me a 0.5%.
Sure,
EVM. This is not a spectrum analyzer.
That's crazy.
It's this whole really this mindset change of considering an oscilloscope as a tool in a millimeter wave type environment.
Interesting. Okay, so millimeter wave, is that like 6 gigahertz and up? Basically, the wavelength is that is referring to?
Right. Yeah. Correct.
Okay. For 5G, is it communicating on multiple? Like, would you have a device that communicates on those multiple bands all at once, or how is it? Or you just kind of pick a frequency, or is there like a handshake that has to happen? How does that? Why are there all these different frequencies? That seems excessive to me, but I'm not defining the spec.
So you can kind of think about it. It's going to go across multiple frequencies as because not all cell towers are going to be 28 and 39 gigahertz wide, right? And and your Wi-Fi networks that's going to be part of your 5G network is going to be different. So what a phone that might be 5G enabled is not going to just sit at 39 gigahertz the whole time, right? I mean, it's got to be able to understand what the infrastructure it's hitting on, and what the speeds are, and everything that goes that way. And so that offers a whole nother thing of difficulty.
So is this going to be like, I don't have cable, right? I just spend all that money on streaming services. So look at all the money I'm saving for shows I don't watch. Yeah, no ads. Is this going to kill like my need for my local cable provider?
I mean,
can I just go full 5G?
It does have potential for that. Like cord cutters, 5G is I won't say the holy grail of cord cutting, but it really does make cord cutting a very viable option. Now you come home and you dock your phone.
Right.
And now your entire house is running across your mobile device on the 5G network.
Yeah,
that's a very possible
okay.
situation.
That'd be really nice. Sounds expensive.
Don't worry.
They'll find a way to charge.
They'll figure out a way to get money from you.
Fair enough. I'm sure they will.
$100 a month is going to go somewhere else.
I'm sure it will.
Don't worry. Don't worry. Your money's safe with other people.
Yeah, safe. Okay. So you mentioned leveraging. It's not, your phone's not going to sit at 39 gigahertz, or your system's not going to sit necessarily at 39 gigahertz the whole time. Are they going to leave up like a 4G infrastructure and have some handoffs between the two, or what's that going to look like?
So here's the interesting thing. Beamforming from the cell tower, pretty easy to do, because you've got this radio unit which is up on the tower with lots of intelligence, and it's doing all the beamforming to hit all the different UE mobile devices out there. Your mobile device, on the other hand, can't do beamforming very well as I'm walking around and carrying it. Beamforming isn't necessarily something that a mobile device can do. So it's doing that more of that omnidirectional antenna type situation. So what the industry is looking at right now is 5G from the tower down to the phone, but potentially you don't need a lot of bandwidth up from your phone, because how many people are really streaming really high definition video from
we don't
phone.
do any media,
so yeah, there's a lot of talk of well, you do 4G and 3G up from the phone to the tower, 5G down from the tower to the phone. And now think about this need for those multiple bandwidths, right? So you've got 39 gigahertz from the tower to the phone, but the phone's talking sub 6 back up to the tower.
Yeah.
I need to see that communication simultaneously, because it's a two-way communication.
Okay.
And to complicate that even further, I could actually be talking to two towers simultaneously with MIMO.
Oh.
So now I need to see this tower's communication, and my phone's communication.
Isn't there some
towers.
black magic algorithms to basically send complementary data from two different towers to the same device? So you can basically you could double your bandwidth just by doubling the amount of towers.
You could double your power in a very black magic Harry Potter kind of way. But yeah, the towers can transmit simultaneously a signal that hits the UE at the exact same time, and kind of like a differential signal in the digital world, right? You get additive power at the UE.
How do you? So many questions. How? I don't know. It's black magic a little bit. How do you actually sync that up? How do you, especially if you're driving down the road or something, right? Yeah. I guess that's the challenge, right?
Well, yeah. Now you're talking about one of the hardest challenges in the 5G space. When you start talking about the front haul and back haul side of 5G, these cell towers now need to be time synchronized very, very precisely in order to now send out the same packet over the air to hit that very limited window of time at the UE to actually get that additive power that's positive versus interfering with each other, which is destructive.
Okay.
Well, and the other thing, I mean, when you look at that, the synchronization of the clocks, or how do you synchronize it? In 4G, you basically had synchronization of the clock the entire path. With 5G, at some point you end up with a cluster where multiple devices are on a single clock.
Oh, okay.
And so you're single clock, and then all of a sudden we're all going to use the same clock here. And so that's a challenge that I think still has working out to do. I mean, it's how do I actually get that done? It's definitely a huge challenge moving in 5G.
Yep.
Because I assume you're not sending out like a separate clock signal, so everyone has to kind of, recover that clock. But if they're all varying distances from the tower, then there's going to be different propagation delays. So there's some.
Yeah, and that's the over-the-air side. Even before you get to the air, there's the synchronization of the base stations themselves, and in places like the U.S., well, we're happy to use GPS.
Sure.
And you can get very high precision timing with GPS.
Yeah.
In other places of the world, they don't necessarily like to be dependent on the United States or Russia's or whoever else's GPS system. So there are other things like synchronous Ethernet for actually doing timing, or precision timing protocol over the Ethernet to actually time those. So there are multiple different ways of actually getting the timing on the front haul and back haul
Okay,
side.
interesting. But that would require like wired connections between all the towers, right?
Well, the thing about it is, I mean, some towers have wireless backhaul going between towers, but somewhere along the way, the tower actually hits a wire.
Yeah.
Sure.
Or actually,
Yeah.
it's a fiber.
Right. Yeah.
So that's where that timing happens. It's at the DU. The DU and the RUs get this time synchronization. Then that time synchronization is propagated over the air.
Okay.
It's that side of it, and you need test tools also to test that.
Sure.
Not only in the development of the equipment, but also in the deployment of these networks at the carriers.
Okay.
themselves.
And your background, you have some network testing background, I understand.
I do have a little bit, maybe 13 years or so of communication test background.
So you were at like there was a group at HP that did it, and they got sold off to JDSU, and now that's Viavi, I think.
Right.
Is that right?
Right. That's
Okay.
true.
And then you come back home.
I've come back to the mothership.
Yeah.
Took a little sabbatical. Yeah.
Cool. Yeah. So we're about out of time. Is there anything else that I should ask? Anything you wanted to cover?
The one thing that I'll cover, Joe mentioned a little bit, and it's my one vicious Keysight plug here, so you'll have to forgive me on it.
Okay.
But, we got to have.
Let me find the mute button. Go ahead.
Yeah. Okay. So now. Yeah. Oh, thanks for turning that back off. So my one vicious Keysight plug is this.
Can we see a reenactment of you pretending that you were muted though? Because you kind of looked like a goldfish.
It looked like I was more eating a Big Mac or some sort of hamburger. Or
Yes.
something,
If you only listen to this podcast, you missed Briggs. I'm going to call it an excellent impression of being muted. So,
perfect.
Sorry.
That's perfect.
Sorry. Go ahead.
my one vicious plug is, a lot of times Joe's mentioned a lot of the advantages of the UXR into these wireless things. One of the things that happens though is a lot of times people think, well, you have 110 gigahertz scope, so you got to pay, for 110 gigahertz, even though the reality
which is a lot
of money, right?
It's not something you buy for your garage.
No.
No.
And so, but I only need, a couple gigahertz is all I need from an analysis bandwidth standpoint. And so on the UXR, Joe's worked on this and they put together a really neat option for the scopes that they call the millimeter wave extension option. And essentially what you do is you buy a scope to 25 gigahertz, and then you buy this little 5 gigahertz wide extension that can go all the way to 110 gigahertz. So you're paying for a 25 gigahertz scope, and then you're also paying for just a small is relative, right? Small for a scope person, very wide for a wireless person, right? But this 5 gigahertz slider that allows you to move around to look at any frequencies. And so what it does is it takes what was a prohibitively expensive scope for guys doing 5G, and all of a sudden it's the same price as what you look at for like a nice spectrum analyzer solution. And then couple that with this really low EVM, you have a really good solution for.
And 4 channels.
And 4 channels. So.
And a scope.
Yeah.
So question on it. I know that the connector side. So if that's the case, you have to have the hardware. I'm not pitching. I actually don't know this. Just for everybody out there, this is not a setup. I just don't know. So I'd assume then that the hardware has to be in there all the way up to 110, even if you buy a 25.
So when we talk about millimeter wave, Well, on the UXR scope, we have a millimeter connector.
Okay, like the 1 millimeter connector.
It's a 1 millimeter connector, but it has adapters that actually go to 292, 185. So, you screw these adapters onto the front with a ruggedized connector. So it's much more robust than a standard 1 millimeter type connector. But you do need to be able to go to these high band frequencies. You need the proper, physical interface that can actually handle that. So if you wanted to go up to 110 gigahertz, you have to have a 1 millimeter connector. You can't do that over a 292 or a 1.85.
Okay.
So you get,
So, we've been doing, people are doing 60, 70 gigahertz with I don't know what the other connector has been. But
it's 185 up to 67 gigahertz.
Okay. So basically now you get to buy new test hardware too, right? Like adapters and cabling. But if you're doing those frequencies, you have to anyway.
Well, so here's the.
Or if you're doing with a signal analyzer, I suppose you have to have that also.
That's true. On the signal analyzer, you have to get the waves into the wire somehow, and at those higher frequencies, you need the smaller diameter. But this is the magic of the UXR, because you get to buy this, let's say a 25 gigahertz scope that comes equipped with 1 millimeter connectors. And what's cool about this is because the UXR is actually calibrated all the way up to 110 gigahertz. So when you buy a 25 gigahertz UXR, you actually are getting a 110 gigahertz scope. And the ability to, just with software licensing, extend that from 25 all the way up to 110, on demand, if you want to say.
Okay.
So you get that capability. So unlike the old world of scopes where every time a new technology came out, it was, well, it's time to trade in or sell my old scope and buy the new scope to do the next new thing.
Yeah.
The UXR is actually the last scope you need to buy, because it really does go from, the bandwidth you need today to the bandwidth that you need not tomorrow or next year, but even for the next 10 or 15 years.
Okay. So I'm going to save this clip, and in 10 or 15 years, we're going to come back and we'll say, hey, the old UXR still works, right, Joe?
Can you please unmute me at that point?
Yeah.
Okay, so we are definitely out of time now. We like to do a stupid question at the end of each podcast. When I remember, sometimes I forget. That's on me, so I'm sorry. If you had to describe 5G, this is a collective question, using 5 words that begin with G, what would they be?
That's tough.
Wow.
No, that's a T.
Yeah. I'm gonna go for great.
Great.
Global.
That's good.
Because you pick a better letter than G.
I know.
No, it's 5G. It has to be,
Gazelle.
global. Gazelle fast. Gazelle fast.
I couldn't think of a better.
You can do hyphen it. Gazelle fast. I don't know.
Yeah.
This is a disappointing end to this podcast.
So please come out to keysight.com and please post your G words for
yes
5G.
Yeah, post them in the comments. eestalktech.com. Yeah. Turns out we fun story. The site was down for a couple weeks because we were using an unmonitored email address for the billing reminders. It was like, all our podcasts are offline. I wonder what happened. And that's so we've changed the email address, so I apologize.
So millions of people were looking for it.
Millions. Yes. No, we get
Oh yeah.
we get decent traction.
Yep.
Yeah.
But you should still tell your friends, because the more people listen, the more we're able to do this. I know it's been a while. So it's been a couple months since we've had a podcast. So we're trying to get back on that monthly schedule, hopefully sooner, but you know how it goes. Life is crazy. I've had like 3 jobs since then. So cool. Well, thank you guys so much for your time, Joe and Brig. Appreciate you coming out. Hopefully we'll see more of you. Make sure to rate and review this podcast in your favorite podcast engine. That helps us a ton. That's how we get found in the search, and that's how we get recommended by podcast engines. Also, tell your friends. The more people listen, like I said, the more we get to do this, and the easier it is to beg time from Joe and Brig, because we want to make this so popular that people just can't resist coming on the show. So that's it. Remember, eestalktech.com or in your favorite podcast delivery engine. I'm Daniel Bogdanoff, and we'll see you next time.